Okay, welcome. We're going to talk about using our fundamental trig identities, as you can see. And this video will assume that you have some background on reciprocal identities, quotient identities, Pythagorean identities, and quotient identities, if I didn't say that. And hopefully this is helpful to you, and let's get started. Okay, we could probably approach this problem to find our 6 trig functions by trying to build triangles, but that's not really that's not really the objective of what we're doing right here. We're really just trying to use the identities and kind of trigonometric gymnastics. So I'm gonna set up a place for us to put our solutions here. Sine of theta is already given. We'll call it theta. I guess it's phi or something like that. We've got cosecant to find, cosine and its reciprocal, secant, and we are going to look for tangent and cotangent. And obviously we're given some of these. Cotangent is -5. Sine, I recognize this as having been rationalized, and you can rationalize denominators or what if you want, but I'm going to go ahead and use the derationalized for sine, 1 on root 26. Okay, first off, we have 2 really easy ones to find because cosecant is the reciprocal of sine. Cosecant must be root 26 on 1. And cotangent is the reciprocal of tangent, so tangent must be -1/5. And then there are 2 viable ways that I can come up with of using our identities to come up with cosine at this point. And one would be to say that sine squared of an angle plus cosine squared of an angle equals 1. And since we know sine, we could put that value in here, square it, and solve for cosine. We would have to then deal with the plus or minus aspect of it. Another option is we know that tangent of theta equals sine of theta on cosine of theta. Or with a little bit of algebraic manipulation here, multiply both sides by cosine of theta, divide both sides by tangent, we get this quotient identity. So at that point I could put in the value for sine, 1 on root 26, and the value for tangent, -1 on 5, and go ahead and turn that into a product, 1 on root 26 times -5 on 1, and I quickly get for cosine -5 on root 26, making secant the reciprocal root 26 on 5. So there you have it. Okay, again, probably a nice approach to this would be to build triangles, but that's not really what we're after here. I'm going to continue to use square root of 24 in this problem, even though we could, of course, change that to 2 root 6. So let's go ahead and set up a place for our solution. Sine of theta, reciprocal of cosecant of theta. Cosine is the reciprocal of secant of theta. I'd encourage you to always set it up this way. 1, it's gonna help having the reciprocals next to each other, but 2, it just reinforces that the reciprocal identities. So what do we know conveniently so far? Cosine root 24 or 2 root 6 on 5 gives me secant 5 on root 24 or 5 on 2 root 6, or we could rationalize that 5 root 6 on 2 times 6, 12, but I'm just going to leave it in that form and assume you can work from there. Okay, now cosecant of -x. I want to know what cosecant of x is. And cosecant being the reciprocal of sine has the same even-odd property as sine. Let's take a look at the graphs of sine and cosecant on a small scale here. The graph of sine looks something like this, and the graph of cosecant then would look something along this line in the green. Not drawn very well. But what I notice is the height of the green graph to the right would be the opposite of the height of the green graph to the left. In other words, this is an odd function. Therefore, the height of cosecant to the left is the opposite of the height to the right. Therefore, cosecant of theta would be the opposite of -5, would be 5. Okay. That makes sine 1/5. And now I'm going to go back to find tangent. Tangent of theta equals sine of theta 1/5 on cosine of theta root 24 on 5. And basically here, the on 5s cancel. And we get 1 on root 24. Isn't that easy? And that makes cotangent square root of 24. Again, all of those could be reduced to 2. All of those root 24s could be reduced to 2 root 6. And you may feel compelled to rationalize the denominator. I'll leave that to the viewer. All right, simplify the expression. You're going to hear me say repeatedly, if you keep following the videos on this chapter, that I'm not a slave to changing things to sines and cosines, but I know many people are by the time they get to this point. So I'm going to go ahead and start just by converting things to sines and cosines. So I have cosine squared of x times 1 on cosine squared of x minus 1. As I distribute cosine squared, that's convenient, I get 1 minus cosine squared of x, but then I get my little thought bubble. I know that sine squared of x plus cosine squared of x is 1, so I wonder, can I manipulate that expression to get this? Sure, if I subtracted cosine squared on both sides, then I get sine squared of x. Let's take a look at another option. How about this? I see this guy and I say, I know that tangent squared of x plus 1 is secant squared of x. Can I manipulate it to get secant squared of x minus 1? Sure, if I subtract this. So I could convert this to cosine squared x times tangent squared x, at which point I'd probably be tempted to change tangent squared into sine squared x on cosine squared x. And once again, we get sine squared of x, and I would suggest that must be our most simplified form. Lots of avenues, lots of routes we can take on this. Cotangent, secant. When I get two trig functions, I do not automatically go to sines and cosines. However, cotangent, secant, if it was cotangent and cosecant, I might try to work with those somehow. They live in a Pythagorean relationship. But in this case, I'm going to go to sines and cosines because cotangent, secant do not live together in a Pythagorean relationship. So cotangent, cosine of x on sine of x, secant, 1 on cosine of x. There's some convenience, and we get 1 on sine of x, which is certainly, I would suggest, more simplified than that. However, better answer, reciprocal of sine of x, is cosecant x. All right, here's when we see our rules on cofunction rules, they look kind of intimidating because there's like 6 different cofunction rules, or 12 different if you want to talk about pi on 2 versus 90 degrees, but they're really all the same. If we introduced a new trig function and I called it star, we could say that star of 90 degrees minus theta is equal to co-star of theta. It's one size fits all. So this is a cofunction. The beauty of these is they just jump out at you. It's like, well, there I am. Use the cofunction rule. There's no disguising it. You're either going to see pi on 2 minus x or 90 degrees minus x. So cosine squared of pi on 2 minus x is sine squared of plain old x on cosine of x. Okay, now perhaps we have 2 different options here. I could turn this into sine of x on cosine of x times another sine of x, giving me tangent of x times sine of x. If I try to turn tangent back into sines and cosines, now I'm just playing trigonometric ping pong. Other option would be, well, the only thing better than getting things in terms of sines and cosines would be getting things in terms of just one trig function. And sine squared, by its Pythagorean identity, can be written as 1 minus cosine squared of x. And that could be written as 1 on cosine of x minus cosine squared of x on cosine of x, or secant of x minus cosine of x. And now we're in that situation where simplified is sometimes in the eyes of the beholder. Which is more simplified? I think I could maybe make an argument in both directions here. Okay, now this one, at this point, this is kind of insulting, but it may give us a nice break. Excuse me. Cosine tangent, they don't live together in a Pythagorean, so I'm going to go to sines and cosines. I'm going to leave this as cosine beta times tangent sine of beta on cosine of beta. Whew, that was a nice break we got there. Just sine of beta. A bit insulting at the level we're dealing with right now. Okay, we got some options here. I could jump right into turning this into cosines, or I could say, since sine squared of x plus cosine squared of x equals 1, 1 minus sine squared of x is cosine squared of x. And I get secant squared of x times cosine squared of x. This is nice. This is the reciprocal. So I get 1 on cosine squared of x times cosine squared of x, or 1. And that's it. Certainly there'd be some other approaches you could use on that, but we ought to end up at 1. Okay, let's say I am just committed to go sines and cosines. I could make this a numerator. Secant could be 1 on cosine of theta, all divided by cosine of theta. If I make that cosine of theta on 1, I can quickly go 1 on cosine of theta times the reciprocal. Gives me 1 on cosine squared of theta, or secant squared, whoops, keep trying to make an x, of theta. How about this? How about I say, well, why don't I turn things into secants? Then I could leave this as secant of theta, all on 1 on secant of theta, making this secant of theta times the reciprocal. So I give no preference to cosine over secant if just the two are given. I might be tempted here to keep secant because it's already in a numerator, but no one trig function gets preferential treatment to me. The bottom line is, if we can get the expression in terms of a single trig function, we should be pretty highly motivated to do that. Okay, here we have secants and tangents and cosecants and cotangents. 4 different trig functions. We're to verify an identity. I'm going to be really picky about identity work. One thing we can do, we can work in each separate side of the equal sign, but nobody from the right side can move to the left. In other words, I can't multiply both sides by sine or divide both sides by tangent of theta. I just have to just stay kind of on my own island here. But I will say this, if I have 3 or more different trig functions, that is an automatic. I'm going sines and cosines. I don't necessarily do it when I have 2 trig functions, but 3 or more, I go sines and cosines. So this can become 1 on cosine of theta minus sine of theta on cosine theta. 1 on sine of theta plus 1 equals cosine of theta on sine of theta. And as I mentioned, I can't just on this side now multiply, I can't on both sides now multiply by sine of theta to get rid of the fraction on the right. The cosine of theta, sine of theta stay to the right. But I could, I guess, distribute. It's going to be a bit of a mess here. I'm going to foil this expression out on the left, And let's see, I get 1 times 1 on cosine theta, sine theta. Outside product, I get plus 1 on cosine of theta. Insides, there's a little payoff there. I get minus, the signs cancel, 1 on cosine of theta. Oh, even a better payoff than I thought. And the lasts minus sine of theta on cosine of theta. All right, well, there's our payoff on this, the biggest part of the payoff right here. And now I have 1 on cosine theta, sine theta, minus sine theta, cosine theta is supposed to equal cosine theta, sine theta. So I'm going to look either side. On the left side, I've got a binomial. I'd want to smash that together to make it a monomial like the right. Or on the right side, try to turn the monomial into the binomial. I think I'm going to work on the left side. My least common denominator between these two terms, I need a factor of cosine. I need a factor of sine. I need a factor of cosine. I've got it. So 1 was already over cosine and sine, but sine was only over cosine, so I had to multiply that second term by sine on sine, giving me minus sine squared of theta equals cosine of theta on sine of theta. And here's where I use my dartboard analogy. If I took you out into a hallway, blindfolded, brought you back in the room, told you I'd hung up a dartboard somewhere, handed you a dart and asked you to hit a bullseye, it'd be pretty tough to do. Keep your eye on the prize. What I'm saying here is take a look at this factor in the denominator right there. I do not want to mess with it because it is exactly what I want the denominator to be. This is so good it's almost cheating. What do I want to happen with the rest of this? I would love this cosine to get canceled. So it has to be canceled by a factor of cosine in the top. But then I'd like another factor of cosine in the top. I sure wish this was 2 factors of cosine. Well, of course it is. 1 minus sine squared of theta is cosine squared of theta on cosine of theta, sine of theta is supposed to equal cosine of theta, sine of theta. Cancel. Cosine of theta on sine of theta, I'm running out of room here a little bit, equals cosine of theta on sine of theta. You're going to hear me talk about this strategy that I call match the factor quite a bit in the coming days, perhaps again on this video as well. It is a fabulous strategy, and it gets us out of some jams and some problems where what we do next may not be quite as obvious as what we were to do on this problem. Okay, verify the identity. Here I have cosecants and cotangents and cosines and secants. And if you were paying attention on the previous problem, I said if I have 3 or more trig expressions, trig functions, I'm going to go ahead and go sines and cosines, even if I create a mess. So 1 plus 1 on sine of theta on cosine of theta on sine of theta plus cosine of theta equals 1 on cosine of theta. All right, very, very few 100% rules, but here's one right there that I'm going to give you that I like to use. This is what I'm going to define as a mess, a trigonometric mess where we have trig functions as a part of compound fractions. Now, I'm pretty certain many of you watching this, because I know a lot of my students have this, would then take the numerator, get common denominator, smash 1 plus sine theta together, take the denominator, cosine theta on sine plus cosine, smash that together with common denominators, a fraction divided by a fraction, flip and multiply. I don't do that. I look at all my terms, 1 term, 2 terms, 3 terms, 4 terms. My least common denominator of those little 4 terms is sine of theta. I'm going to multiply by sine of theta on sine of theta. Why can I do that? Because sine of theta on sine of theta is just a fancy form of 1. That's our foo-foo. It's fancy form of 1. Sine of theta on top, sine of theta on the bottom. Look what that does for us. Distribute sine of theta plus 1 over, sines cancel, cosine of theta plus sine of theta cosine of theta is supposed to equal 1 on cosine of theta. All right, think back one slide. I would love to have a factor of cosine of theta. Now, you may have been looking at the left side and said, hey, look, I can factor a cosine out. Well, yeah, there's a lot of things we can do on the left. I could multiply top and bottom by tangent, but there isn't much sense in it. I'm driven by the right side, my target. I want to have a factor of cosine in the denominator, and I have a factor of cosine in the denominator. Sine of theta plus 1 on cosine of theta times 1 plus sine of theta. And before we get ahead of ourselves here, now I have a factor of cosine of theta. But again, I really want to stress this. I was driven by the left side, not by what I can possibly do in the right side. I try not to make moves just for the sake of making moves. I try not to do something just because it's possible. So hopefully, once I have that matched factor, everything else sorts itself out, and we can quickly see they do. The other terms do, factors do sort themselves out. I get 1 on cosine of theta equals 1 on cosine of theta. All right, so hope that's helpful. Let's continue on. All right, here I've got on the left a bunch of sines and cosines. On the right, not sines and cosines. So I think I'm going to take this right side and I'm going to make that sines and cosines. Secant 1 on cosine of theta. Cosecant 1 on sine of theta. And on the left side, I think I'm going to go ahead and smash that into a single fraction. Going to be a little bit messy here, but I need a denominator of sine factor and a cosine factor. So my least common denominator has a factor of sine and cosine. This was already over sine, so I had to multiply this by cosine on cosine. This was already on cosine, so this had to be multiplied by sine on sine. So that's minus sine of theta, cosine of theta minus sine of theta. Okay, I'm going to go ahead and distribute. I'll tell you what I'm not going to do at any point. I am not going to ever cancel one of these because I've matched those factors. Such an important thing to keep our eye on the prize. So somehow or another, I need to work with the numerator to turn it into 1 without messing around with that sine cosine denominator. I'm going to go ahead and distribute the numerator. I get cosine of theta sine of theta plus cosine squared of theta. That's a little bit promising. Minus sine of theta cosine of theta plus sine squared of theta, that's what I was looking for. All on sine of theta cosine of theta equals 1 on cosine of theta sine of theta. So can I get 1 out of this? Boy, it's tempting to do it in one step. I would recommend not to. Here we have cosine sine minus sine cosine, so that is 0. So I can get to cosine squared of theta plus sine squared of theta, all on sine of theta cosine of theta equals 1 on cosine of theta sine of theta. So let's talk just for a moment. Why not do both those steps, both those in one step? Remember, on an identity, we're not just driven by getting to the final solution, 1 on cosine of theta equal, or 1 on cosine of theta sine of theta. Our job is to show the viewer in a very easy to follow process. And if we jump from here straight to this next step, we may lose the viewer. Like, what has happened here? On identities, we really want to take baby steps, and I'm gonna enforce that pretty strictly. So now we got cosine squared plus sine squared. The viewer should, with a little bit of knowledge, know where that came from. 1 on sine of theta cosine of theta equals 1 on cosine of theta sine of theta. So there we have it. So more trig identity fun. Okay, factor and simplify. Almost wish they wouldn't have said factor. One thing I would never do on this problem is turn things into cosines. We're already in a single trig function. That's as good as it gets. It doesn't matter which of the 6. But they say factor, and we're going to factor by grouping. I'm going to take out a secant squared of x out of the first 2 terms, giving me secant x minus 1. If factoring by grouping is going to work, I need to get another one of those. Let's see if we can. Can I get that? I can if I factor out a negative 1. So I pull this mess out. Secant of x minus 1 times secant squared x minus 1. And there's a squared trig function with a 1. Thought bubble. Tangent squared of x plus 1 equals secant squared of x. Can I get a secant squared of x minus 1? I sure can if I subtract 1 on both sides. So that just becomes plain old tangent squared of x. And you can play around with this, go sines and cosines and try, but I think you would be hard pressed to get this any more simplified than that. And sometimes that's kind of the frustration. When I give a test and I ask to simplify, I give problems that simplify down to a point where it's pretty clear what the intended solution should be. So hope that's helpful. We're going to have a lot more identities that we're going to add to this over the next couple days, the next couple videos. So please stay tuned. For those of you that are just visiting guests and not from the class, you can follow along by sections on my Hananiga High School Pre-Calculus website. That is at www.purpleshirtednerd.com. So please feel free to check that out at any time you'd like. Thanks for visiting.